Today we're looking at battery protection and seeing what we can do to protect our circuits from reverse polarity. Reverse polarity is what happens when you insert the battery in the wrong way. It seems like something simple we will never do, but it happens to all of us, even happens to the best of us even. I have 3 simple circuits here I want to go through and describe what are the pros and cons of it and how they might fit into your design. I'm using Multisim here to illustrate the fact, but I will be placing this circuit only in breadboard, and for reasons why I'll tell you later. Let's start off using a simple diode. This method is probably the one you've seen the most and probably one that just gets recommended a lot, saying, oh, just put a diode in, it's simple and you'll only face a small voltage drop. Well, this small voltage drop is quite large in fact. Let's simulate it. So we have a BAT165A, we are running a circuit. In reality this won't consume 562 milliamps for an LED. Standard value we put here usually is 3/3, so we'll put that. You see we have 3.9 going through, instead we have a voltage drop of 0.3. This isn't that much in fact, and if this was a true battery like a lithium ion or something, we still have most of the capacity left due to the battery's curve. Let's take a look at this datasheet. We're on the datasheet of the BAT165, a simple Schottky diode, and it's something you can expect with Schottky diodes with low forward voltage at around 0.3, 0.4. But as you can see, we have a forward voltage. If the current is 700 amps, we get a typical of 640, 740 millivolt. Here we look further down into the datasheet and we realize that there's more to it than just what was initially shown to us. We see that at different values, so for example, assuming 10 milliamps, we get a typical voltage drop of 300 millivolt. This then goes up the further current you decide to draw through. And if we go to the teetering edge of it of around 750 or 500, we get a very high voltage drop of around 0.7 at its maximum. Back in our simulation, as you've seen before, let's increase this slightly. So we're going to play the simulation, we're going to adjust the values, and see the more, as you can see, the more I decrease the more you see the voltage drop occurring. And we are getting a much higher voltage drop the lower. All the way down to here, we see at 5.5, we get a voltage drop of around 0.6. Back in our datasheet, if we have around 500, we get a 0.6 drop. So it's around in between these two areas. That directly corresponds to what we're looking at. So if you remember the curve I just showed you up on screen, you can already see that at certain areas of the battery, we have most of our energy. This is really crucial in kind of wearable applications. So for example, if your wearable device assuming this amount and you've decided to place this in here, or you've had a much larger, chunkier Schottky diode or something, you'll notice that, oh, I'm already in that long period. I've already lost some percentage of my battery. It's not that ideal. Maybe for smaller projects and things, maybe if you're not in that much, probably isn't ideal. So if we put it back to 330 here, you know, 0.3, we're not too bothered, but of course standard. This is just a standard characteristic of the Schottky diode. It's something we can't avoid. Of course you can use regular diodes as well, they just work just as well, but you see they'll tend to have a higher voltage drop across. So even though these are more expensive, I think it's much more worth. So you've seen our circuit running in forward bias. It's the diodes in the right orientation, voltage current can pass through. What if we place our battery at negative value? So we are simulating a reverse event. You'll note here that it is negative 4.2. But we'll look at a physical application now, and we'll look at why this simulation might not be true, might be not what you expect. Let's take a look at it. So I have a little circuit set up, and I do apologize for horrendous quality, but I am just using my webcam, and this is my desk setup. So what we have here is we have a diode, resistor, our LED, jumper cable, and we set ours to 4.2. We have a maximum current of 0.50 amps coming out. We have a power supply. We are connected through to the positive to the negative. So this is in forward bias. Let's turn this on. We get our LED on. This is fantastic. This is what, very simple, nothing to panic about. So I'm going to turn on my multimeter. Let me get that adjusted. We're going to take a brief measurement. So the wrong way. So I've got my multimeter set up, and we're going to take a brief measurement here. We are going to take from the the positive and the negative, and we see we have a voltage drop of 0.7, which is kind of what we expect. You can see it's just flickering around because I don't have a stable connection on it. So this is kind of what we expect, and that's normal, that's fine, this is what we expect. So if you can imagine, if we use this in our application, we're losing quite a big chunk from our battery. Turn that off. And our power. Let's switch the leads around. So I'm going to switch it back on, and we are simulating for what is a negative battery. So we switch this back on, and we're going to do the same thing. We get nothing on our output. Good. We get here negative 4.2 volts. So there's nothing happening over here. We get negative. So it's essentially blocked. So as you remember from our previous simulations, though, we saw that we might be getting negative 4.2 volts on the output, which is definitely not the case here because it showed 0. It showed a negative 4.2, which is not the case here because it showed 0. Back to our second circuit here, we have a N-channel configuration. So we have an N-channel FET configured on the low side of the circuit, and we're essentially just stopping this middle, making the circuit complete, I guess, connecting it to ground. So putting in the negative configuration, we have our vent. There's nothing, our LED is off. It stays off. Let's apply positive, and you see that our LED is switched on. We see that there is no problem here. We don't have a voltage drop. We draw a certain amount of current. Probably will get a voltage drop over here. Place a voltage node. Save voltage, 714 millivolts. Okay, irradiation, and you can build the circuit by yourself to see what you actually expect to get out. Now, it may be all good, but the problem with this circuit is that it's on the low side, and this means we'll experience a small voltage drop across here, which can do the rest of our circuit if we're not careful. So this again, whilst N channels are, I believe, well, they're fairly decent, I believe certain RDS on characteristics, they form better, or worse, I cannot remember now. Though, just the fact of experiencing a small voltage drop across the ground may skew our results. We're not really willing to do that. Moving on to our final configuration with a P channel FET. This is the one I tend to use the most in my applications and designs. And it's for reasons that, well, I'll show you here. We have 4.2, about 0.2 volt drop, and we're getting about 327 milliamps out. Though, if we reduce the current, see, we barely get a noticeable drop in this application. So for simple things, it's really not too bad. But why is this? Again, it's the RDS on of this application, of this FET itself, that we need to calculate and know to what we expect our voltage drop supposed to be. So let's have a think about it. Let's look at the datasheet for this. So looking at the datasheet for this, we have quick reference data. We see an RDS on of well, not 1 amp or an amp. We have 0.25. So what's that? 250 milliohms, I guess. No, that's quite large, but let's see if we can find spawn. Here we go. So this might be a bit more helpful to us. So as we can expect a 0.5 amp, we get around an RDS on 0.4 max and 0.33. At 1 we get 0.22 to 0.25. Let's take a closer look at it. So for the sake of simplicity, we're gonna try to get a larger voltage drop so we can clearly see what we're looking at here. Maybe around here. So this is 628 milliamps. What does this mean? So we go back to our datasheet. Around there, let's put 0.4. We're near this value, and we might as well take the worst case. So I do 628 times 4. It's about 0.5, our answer, which quite closely corresponds to this value looking at. So we can already check this out and say, oh, okay, so this is exactly how we determine what is our voltage drop going to be. So I've changed the values again. 327 milliamps coming across here into our LED. In real life, I think this thing would blow. And we'll experience a voltage drop about 0.2, something like that. Of course, we're going to plug this in again, so we're going to use our datasheet value 0.4 to 327 milliamps, and we get a value of 0.13, which looks very closely to what we're expecting here. So this is usually how you would calculate our values for this in this case. Now that we know all this, why didn't we put the FET on the high side? We come back to our FET here. If we had placed this on the high side, I'll show some circuitry here, we can see we need a bit more extra circuitry here. This is because due to the characteristics of the N-channel MOSFET, we do need a high voltage at the gate than the source of our FET to drive it. So being in this case, we won't have a high enough voltage to simulate it, and this would cause issues. And this would cause issues here. So this is just characteristics that we need to follow, have higher voltage, and usually they put some charge from circuitry, maybe this. It's one of many solutions really. So it all depends what you're really looking into. So this was just a quick video on the different ways of batching. Again, I'm using Multisim, and it's a great tool just to simply have a play around, simulate some stuff, and see what you're expecting to get out of it. I use it quite a bit just for simple circuits if something I'm not too sure about, or just want to test some logic levels or whatever. So it's not a bad idea. Highly recommend it out. Overall, I'd say I'd use the P channel MOSFET as in most of my designs and configurations, just because nowadays you can get them for so dirt cheap, really, and for what, sometimes you get it for 50 pence or something. It's one component, and it's going to save you from blowing up the rest of your circuitry. Or just don't put in the battery wrong.